before we even worry about radar, let's just get into the basics of what we're doing when we plot, like how we actually analyze motion when it's all relative to us. And we do that through vector triangles, which are just trigonometry. You probably, I'm certain you've got some familiarity with this, because if you took a physics class in high school, it probably went into vector triangles. If you took a trig class in high school, it probably did. That's less likely. Usually trig was more static stuff, but they would have been totally within their rights too if they did. Certainly any kind of physics classes in colleges are going to go into it, and like videos on the internet about Einstein would have stuff like this. Just really basic, relative motion is just how one object moves relative to another. So it's always based on the observer, or it has to be. Who the observer is can change. You can change who you're thinking about there. But if this is us and we're still, and then we have another object right here that's moving this direction at, let's not even use knots, let's just say 10 miles an hour. Well, from our perspective, it's moving that way, 10 miles an hour, right? From its perspective, it is essentially stationary, and we're moving that way at 10 miles an hour. I don't know why I keep doing that. Seconds. If we're here and we're moving this way at 5 miles an hour, and then it's here moving that way at 10, then from the point of view of us, we're stationary. It's moving this way at 5 miles an hour. From the point of view of them, they're stationary. We're moving that way 5 miles an hour. If we took a third person, both of them are moving this way, just this at 10 miles, this at 5 miles. But to us, this one's moving back at 5. For this, it's moving back at 10. This is not complicated stuff, obviously. But then we get into situations like this. We are moving this way at 10 miles an hour, and they are here moving that way at 5 miles an hour. Now it gets a little more complicated. We're moving at different, in different directions, not just either in the same direction or in a reciprocal direction, but at angles to one another. And it's a lot harder to say with any certainty what its actual motion, what our motion is relative to one another. Now, in physics, what you would have done is you would have done trig to break this 5 mile vector here into a lateral or a vertical and a horizontal component, and compared what those two are, and then found a horizontal and compared it. It would probably be like 3 or something, and compared that to this horizontal motion. Or we could have broken the 10 down, done the same, and just made it relative to the 5. But we're going to look at it slightly differently. Let's take this problem of us moving this way at 10, then moving that way at 5. If we make it a little bit bigger, just so we can see better, say that's us, and this is our motion. Now, let's take them, and we're going to place them starting over here. Oh, wait, no, sorry. We're going to place them starting right at the end of our vector, and their motion is going to be going this way, like it was before. And now you can see, we'll label this 10 and this 5. This is not representative of our actual relationship to one another because they're somewhere over here. They're not right in front of us. But if we place them right in front of us and then have it continue this way, we can connect the dots between the two. And right there is the relative motion between the two of us. What direction it points is dependent on who we're dealing with. If we're talking about ourselves and we're trying to describe what their relative motion is, what their motion is relative to us, then, oh, I'm sorry. This is bad. We're going to set it up again. I was kind of in the radar mindset. I have to. Yeah, so this is us, and then this will be them on their motion. We're going to have them both start at the exact same point. And then we're going to connect the dots between the two. I'm sorry that I confused you there. Ignore this. We have them both start at the same points, and then this hypotenuse of the triangle here, that is the relative motion. And which direction it is depends on who we're looking at. So if we're talking from our own perspective and we're trying to think about their relative motion, we would point it in this direction, and I'll get into why later. And what that means is that from our perspective, even though in reality they're going this way at 5 miles per hour, from our perspective, we are stationary and they're going this way, so at a slightly different angle at a different speed. And given the fact that this is longer, I'd say it's going to be like 12 miles per hour. A faster speed at a different angle than their true speed, or than their true direction. If we were talking about from their perspective, well, then the exact opposite is the case. They're stationary and we're moving this way at 12 miles an hour. All we need to do in these situations where we have two different vectors headed in different directions that aren't perfectly reciprocal or parallel to one another, or if they're just not in line with one another, is we can take take both vectors, set them based on the same starting point here, and then connect the lines between them. Now, obviously, these two lines need to be proportional to one another. I just drew them any random length, but technically it should have been more like, if this is 10, then 5 would be about half of that, so that would be 5, and then we would connect it. But this is just to represent that basic triangle there. Now, if it seems kind of vague and general, I mean, we go whichever way we go, they go whichever way they go, and then we connect the lines together and then have their relative motion point generally towards them. I'll draw out another here. So like, let's say we were headed this way and they're headed like that way. Then we could bring the two together. And let's say we're 12 and they're 6. Set 12 here. Set 6 is about half of it there. And then we'll connect it. And then once again, their motion relative to us would point that way, and our motion relative to them would point this way. If that all seems kind of vague and general, we should give these vectors names. That way it gets more solidified. And the way we're going to name these vectors is we're not naming the vectors, we're naming the vertices, or the points where the vectors end. So doesn't matter where it is. This starting circle here we'll label E. And then whichever vector is our direction, is our course and speed, if we're using nautical terms, we're going to end that point with R. And whichever one represents their motion, we're going to label that point M. So here's the starting point of both vectors. Our vector ends in an R and their vector ends in an M. Therefore, we could name our vector the ER vector and theirs as the EM vector. The way we always remember this is ER, our, and EM, them. Our vector, them's vector. And then what's the last vector called? RM. Well, that's just the relative motion vector. And if you're now, if you still don't know what direction RM goes, it always goes from R to M, because ER is not necessarily our course. It's the course we've chosen to be setting as the baseline. Because what if you were doing this off of two different ships and you weren't on either of them? Well, then you have to set one of them as the baseline. So whichever one you set as the baseline is always going to end in R, and therefore R will always go to M and represent the relative motion of the other. If we wanted to analyze the relative motion of this object from the point of view of this one, then we would just take the same diagram again. This would still be E, but then we would set this is R and this is M. And this, if this time relative motion goes that way, now relative motion goes that way. It's important to note the two ships here are not doing anything different. This one's still going this way and that one's still going that way. But this diagram shows it from the point of view of this ship, and this diagram shows it from the point of view of this ship. And by doing that, you will get the same direction and speed of the relative motion, but it will flip if it's going this way or this way. I know it still is kind of abstract. The next video is going to put this in much more concrete terms because it's going to go into something you've already learned.